Uh, Hello, I am Khaja Asifullah, lecturer in chemistry from Government Degree College, Palakkuma. Today, we will take chapter B of elements from BSc first year, semester 1. It is part 1 means first lesson for this chapter because it is a lengthy chapter. We may have more than 1 or 2 lessons classes. We know that till today about 118 elements are known to us. These elements are arranged on the basis of their atomic number, increasing order of their atomic number. During the process, elements with similar electronic configuration and similar properties are arranged one below the other, forming groups and periods, and thus they form a table called as modern periodic table or long form of periodic table. The basis of periodic table is nothing but atomic number or electronic configuration because the periodic law says that properties, both physical and chemical properties of elements, depend on their atomic numbers, or more correctly, on their electronic configuration. Hence, when we arrange these elements, these 118 elements, in increasing order of their atomic numbers, all those elements having similar properties will be arranged one below other, thus form a group. In this way, many groups are formed. Totally 18 groups are 8 A groups and 8 B groups are formed in the periodic table. Therefore, we have 18 groups and 7 periods in the modern periodic table. If we study the long form of periodic table, or which is also called as modern periodic table, we have different types of classification of elements, like the classification based on electronic configuration, classification based on blocks like S, P, D, F blocks, or classification based on the properties of the elements, etc. Today, we will consider the classification based on the sublevels SPDF, how they are classified into blocks S, P, D, and F. Is on the basis of the last or differentiating electron of a particular element which enters into the particular sub-level. For example, if that for a particular element, last or differentiating electron enters into S sublevel, that will be called as S block element. If there is an element in which last or differentiating or outermost electron enters into P sublevel, then it is called P block element. Similarly, D and F block element. Therefore, because today's topic is D block elements, we can define d block elements in such a way that elements in which their differentiating electron, that is last or outermost electron, enters into d sublevel. Then these elements are called d block elements. I think you understood that. The last electron of an element, if it enters into d sublevel, then it is called d block element. For example, iron, copper, nickel, gold, silver, platinum, etc. All these elements will have the last electron in d sublevel. Today we will consider or we take chemistry of d block elements. Before that, you should remember that just the differentiating electron or the last electron only makes the difference, and it is responsible for most of the physical and chemical properties of an element. For example, if we consider hydrogen from first group, the electron enters in s sublevel. Then we have beryllium or then aluminium, etc. If we consider beryllium and aluminium, there is difference. Beryllium, lithium, etc. belongs to S block, whereas boron, aluminium, etc. belongs to P block. Similarly, we have D block elements. Generally, these elements are also called as D group elements. D group elements. Again, they are divided into 8 groups, 8 D groups, starting from first D group to 8th D group. Here, these elements are also divided into series. We have 4 series of D block elements, and every series will have 10 elements each. And these series are named as 3D series of elements, 4D series of elements, and 5D series of elements. Similarly, 6D series of elements. Out of these, 6D series is still incomplete. Most of the elements are discovered, but few are still under analysis whether they are found naturally or not. Then we have 3 complete series of these elements: 3D, 4D, 5D, means 10 into 3, 30 elements plus 4, 5 elements. Not exactly 40, but we expect them to be 40. Therefore, we have nearly 40 elements in D block, and they are divided into 4 series and 8 groups. Series means every period will have 10 elements, because in first series, that is 3D series of elements, electron will enter into 3D sublevel. In next, it enters what differentiating electron enters into 4D sublevel, therefore it is called 4D series. Similarly, if differentiating electron of element enters into 5D sublevel, it is called 5D series, and then 6D series. Here, the electronic configuration of these elements is ns1 1 to 2, n minus 1, be 1 to 10. What is the meaning? That here both nth level and n minus 1th level is incompletely filled. What is nth level? It is nothing but outermost orbit or outermost energy level is incomplete, because in that nth or outermost series only s sublevel will be having electrons, that to 1 or 2. In few elements it will be completely filled, and in few it will be only half filled. Whereas penultimate shell of p block elements, that is n minus 1th shell, is also incompletely filled. What is penultimate shell? Just before outermost shell, an orbit or energy level or energy shell, it is just before the last or outermost orbit is called penultimate shell. So last and penultimate shell both are incompletely filled here. Only in one group of elements like zinc, Ag and cadmium, n minus 1 sublevel is completely filled. Now, if electron enters into 3D, there can be 10 electrons, that will be entering here one by one. Therefore, we have 10 elements. For each electron, one element. Similarly, 10 electrons, 10 elements, 10 plus 10 like that. So the general electronic configuration of these elements you have to remember as n minus 1 d 1 to 10 ns 1 to 2. Coming to the atomic numbers of these elements. Here we have series, 3D series, 4D series, 5D series, and 6D series. Okay, if you take third B group, fourth, fifth, that means these are starting from third B. Then after 8B, we have first B and second B group of elements. So first and second B group are on the right side, and from third B group the series starts. Whereas 8th group or 8th B group consists of 3 vertical columns. So 3 for the 12 elements belong to 8th B group, whereas all other groups will be having 4 elements each. Now, first series of these elements is called as 3D series. Here we have scandium. Its atomic number is 21. Then titanium 22, vanadium 23, chromium 24, manganese 25, ferrous or iron 26, cobalt 27, nickel 28, copper 29, zinc 30. Zinc is the 30th element of the periodic table, but in the E block element, the first series starts from scandium 21 and ends at zinc 30. Coming to the next, our second series, which is also called as 4D series of D block elements: yttrium, zirconium, niobium, molybdenum, technetium, palladium, silver, cadmium. In this way, here the atomic numbers start from 39 and ends at 40. Why? Because after zinc we have few more elements, which are 8 elements. So when we add 8, 10 plus 8, 18 to 21, we get 30. Similarly, again we add 18 to 39, we get 57, which is lanthanum, osmium, etc. to mercury, platinum, gold, mercury, etc. Here, after 57, there will be 32 elements, 2 elements from S block, 6 from E block, and 14 from F block. Therefore, totally 32. We have to add 32 to 57 so that we get 89. So, third series or 5D series start from lanthanum 57 and ends at mercury 80. Here it will start from 89. As I told you, here there are few elements which are still to be confirmed that they are naturally occurring elements. Therefore, we can also say it is an incomplete series. So this was about the atomic numbers and the elements present in every series of D block elements. Let us consider characteristic properties of D block elements. What is the meaning of characteristic properties? These properties are particularly belong to D block elements. Few of them I am listed here are: first, electronic configuration. Next is variable oxidation states. Next is magnetic property. Next is catalytic property or catalytic activity. Next is complex formation property, etc. Many more properties like color property, color of the ions of the block elements, interstitial compound formation of interstitial compounds, and few more we are not considering in today's class. We will try to complete these 5 properties or cover these 5 properties in this lesson. Okay. For that, let us consider first the electronic configuration. Just now, I told you the general electronic configuration of these elements, which is nothing but n minus 1d, 1 to 10, and ns 1 to 2. Then what will be the electronic configuration of first series of these elements? Or it is also called as 3D series. Here, let us consider scandium, which is the first element, titanium, then vanadium, chromium, manganese, ferrous or iron, cobalt, nickel, copper, and zinc. These are the 10 elements of first series of D block elements. Now, if we consider these elements, first scandium, the atomic number of scandium is 21. We know that the standard form to write the electron configuration, that is organ. Then 3d1 4s2. We write organ, 18 electrons will be covered here. Then how many remains? 3. Out of 3, 2 will enter into 4s, and 1, that is the last electron, enters into D3d. This is the last electron of scandium which is entering into 3d. That's why scandium belongs to 3d block of element. Similarly, up to these 3, our third element, vanadium, S is completely filled and the last electron is entering into D. Then it should have been 3d4 for S1 for chromium. The electronic configuration of chromium should have been argon, that is 18 electrons, then 3d5 4s1. Here for every element you should first consider argon because 18 electrons are covered there. Then the remaining, that means after 18th electron, how many electrons are remained? We are arranging them into either S sublevel or in D sublevel. Here in chromium, if I write the electronic configuration of chromium as 3d4 4s2, it will be wrong. The chromium is having atomic number 24. After argon means 18 electrons, we remain with 6 electrons. I can write 4s2 3d4, but it is wrong. I have to write 3d5 4s1, which is the correct method. Why? Because there are certain rules to be followed to write the electronic configuration of elements. What are those rules? Among those rules, we have one n plus L rule, where n, that is small n, represent principal quantum number and small l represent azimuthal quantum number. The sum of these two should be least, then only that is considered as stable or correct way of writing the electronic configuration. Here there are two such elements in which we may get confused. One is chromium with 24 as atomic number, another is copper. 29th element or its atomic number is 29. Copper, if we write, because it's having 29 electrons, if we write argon, 18 electrons will cover, then the remaining 11 electrons, I can write it as 4s2 3d9, but it is wrong. The correct method is writing 4s1 3d10. If I write it like this is completely filled and it is half filled. Due to that, it will become more stable. Okay? Copper becomes more stable and it obeys n plus L rule during writing the electronic configuration. So it is the correct way. If anybody write 3d9 4s2, it would be wrong. So for both chromium and copper, these electronic configurations which are shown here are stable electronic configuration, and this is the correct way to write their electronic configuration. Now coming to zinc, after 29, 30th electron is last electron for zinc. Argon means 18 electrons plus 12 electrons. Out of 12, 2 will enter into S sublevel and 10 will enter into E sublevel. So in this element, the electronic configuration is complete, or it is completely filled. Therefore, after a few minutes, we will take the color or magnetic property there. We can understand, we can remove 4s2 electrons. Therefore, it will be having no unpaired electrons. Therefore, it is important to understand that these two electrons can be removed. Okay, from copper, this electron can be removed. These two electrons can be removed. Therefore, the common oxidation state for these elements may be +1 or +2. Most common is +2. Okay, now at present we are talking about electronic configuration. So this was about the electronic configuration of first series or 3D series. Next is 4D series. Again, we have to follow the same thing. Here we know that molybdenum and silver, there will be some deviation in writing the electronic configuration. Here, after writing 36 electron as krypton, For yttrium, totally 39 electrons it will have because its atomic number is 39. So out of 39 electrons, 36 will enter into krypton. Therefore, we are writing only 3 electrons here. So the exact electronic configuration of yttrium will be so krypton, then 4d1, 5s2. Similarly, for zirconium, 4d2, 5s2, etc. Coming to the molybdenum, there arises the problem again, as we did in the chromium. In the case of chromium, we have to write like this: 5s1, 4d5. Similarly, for silver, we have to write like copper: 3d10, 4s1. Here for silver, 4d10, 5s1. Okay, in this way we can write. Again, these 2 electrons from s sublevel can be removed from most of these elements. Therefore, the most common oxidation state of these elements is +2, and that is the most common oxidation state for d dot elements. Next is the third series are 5p series, lanthanum, hafnium, etc. to mercury. Again, the same problem arises with wolfram, and then in the case of gold. Okay, again we have to write xenon, then etc. Then these 6 extra electrons are 6 electrons out of 6. 5 will enter into 5d and 1 will enter into s. We cannot write 6s to 5d, 4 is against the rules. And because these elements are more stable, therefore we have to write the stable electronic configuration for wolfram and then for gold. So starting from copper, silver and gold are stable compounds. Similarly, we have the next series, again the same similar, because as I told you earlier, in periodic table we have arranged the elements, or we have classified the elements on the basis of either on the basis of atomic number, or you can also say that they are arranged in order of their electronic configuration. Elements with similar electronic configuration will come one below the other forming a particular group. So this is third B group element: scandium, yttrium, etc. Scandium, yttrium, lanthanum, hafnium. Similarly, third, fourth, fifth, sixth, seventh, these 8 group, first group and second group. First group, second group. Third, fourth, fifth, sixth, seventh. Like. So we have scandium, then yttrium, and lanthanum, then actinium. Like. Now, the next property is called variable oxidation state. What is the meaning of variable oxidation state? Let us first consider what is oxidation state. Oxidation state or valency or oxidation number. We can say that it is nothing but the electrons which can be removed or added or shared by an atom of an element. Is called oxidation number or oxidation state or valency of the particular element. For example, if we have scandium, okay, scandium has 21 as its atomic number. Why I am giving definition of of oxidation state in three terms. Means the electrons that can be removed, or that can be added, or that can be shared. Because few elements have tendency to lose electron, few have tendency to gain electron, and some elements are there which can share electron. They neither lose nor gain. Therefore, we have to define in terms of electron like that. D block elements are metals, and you know metals always tend to lose electron. Non-metals like sulfur, oxygen, chlorine, etc. gain electron, and few elements like carbon, silicon, etc. they share electron. Here, these are metals. All elements of the block elements are metals, and metals tend to lose electrons. Therefore, oxidation state of these elements is nothing but the number of electrons that can be lost by a particular metal or element. And when electrons are lost by an element, we assign positive sign. Therefore, we can say the oxidation state of scandium is either +1 or +2 or +3. But here you should remember we cannot easily remove this alone. That means the electron present in 3D. But it is easy to remove these two electrons. Therefore, in the case of scandium, we have 2 and 3 as oxidation state, not 1. So this is in Roman letters. Then when the oxidation states are given in Roman letters, we need not write plus sign. And this is standard form to write oxidation state. It is in IUPAC system. So when we write Roman letter, don't write plus. If we write normal Indo-Arabic letters, then we have to represent the sign also. Either it is plus or minus. Here, because these are elements, we have to write +2, +3, +4 like that. Because we are using Roman letters, no need to write plus. So now let us try to understand variable oxidation state after understanding about the oxidation. Variable, what is the meaning of variable? These elements exhibit different oxidation states in different compounds. In one compound, scandium exhibit +2 and another +3. Okay. Let us consider copper here. Copper exhibit +2, +3, +1 also. Copper mostly exhibit either +1 or +2. In the case of copper, it is +1 and +2. Cupric, cuprous. Here, in second element, we have 2, 3, 4. Here it is because of 2 + 2, 4. 2, 3, 4, 5 in the case of vanadium. Chromium 2, 2, 6. This is called variable oxidation state. Means a particular element can exhibit different oxidation states in its different compounds. Okay? Chromium Cr +3, it is 3. Cr +6 is +6. Manganese +2, +3, +4 like that. If we consider manganese dioxide, MnO2, oxygen can gain 2 electrons. 2 oxygen atoms are there, 2 into 2, 4. All those electrons are given by manganese. Therefore, in MnO2, manganese dioxide, Mn exists in +4 oxidation state. In KMnO4, it exhibits +7. Like that in chromium, CrCl3, 3, FeCl2, 2, FeCl3, 3. Ferrous can form Cl2 or Cl3. If it forms Cl2, then its oxidation state is +2. If it forms Cl3, its oxidation state is +3. It is ferrous, like that. So these are different oxidation states. Are these are exhibited by one element in its different compounds. This is the reason why we say variable oxidation state. So nearly all three-block elements exhibit variable oxidation state. Means they have more than one oxidation state. All these oxidation states are not exhibited in one compound. They exhibit one of the oxidation state in one compound, other in other compound, like that. V2O5, vanadium pentaoxide, V2O5 means 5 oxygen atoms are there. 5 to the 12 means 10, because every oxygen atom gains 2 electrons. So 10 electrons are given by 2 atoms of vanadium, means 10 by 2, 5. Each atom will have 5 as oxidation state. All electrons are given or lost, therefore +5. Okay? In V2O5, its oxidation state is +5. In this way, we have to understand. Similarly, now, before this, we can understand the oxidation's most common oxidation state also. This is 4s2. Wherever 4s2 is there, those 2 electrons can be removed. Therefore, they have common oxidation state as +2. So, in most of the D-block elements, +2 is most common oxidation state. Is most common means nearly all elements exhibit +2 oxidation state. Similar is the case with next series. Again, the variable oxidation state we have nearly all in all series. But one thing we have to remember, that this element OS means osmium exhibit the highest oxidation state +8. Okay, here in this series, which is 5D series, starting from lanthanum, we have osmium. Osmium exhibit +8 oxidation state. Now, next property we can take is magnetic property. Because magnetic property, let us understand what is magnetic property actually. You know that certain substances are attracted in magnetic field. What is magnetic field? It is nothing but a field around a particular object called as magnet, due to which it attracts certain type of elements and compounds. For example, elements like iron, cobalt, nickel, etc. are attracted by magnet. And magnet is generally made up of iron. Here, on the basis of that, we can say that substances are mainly of two types. One is magnetic, another is non-magnetic. Means the substances which are attracted towards the magnet are one type called as magnetic substances, and those which are not attracted, are on which magnetic field has no effect, those are called non-magnetic. As we know, iron etc. are magnetic substances, or they are ferromagnetic, they are called. Similarly, non-magnetic like paper, wood, plastic, etc. Coming to the substances, we have magnetic property due to the electrons. In modern theory, that is called electronic theory, which explains that the magnetic property of a substance or an element is due to the spinning of electrons. It is due to the spinning of electrons. There are many theories which explain magnetism, like Weber theory, etc. Ewing theory, Weber theory, etc. Here, in electronic theory or modern theory, it says that the magnetic property of any substance, whether it is element or compound, depends on the spinning of electrons. Every electron will spin on its own axis and produce some magnetic moment or magnetic field. Every electron. But we know that if there are two electrons in one orbital, these are called paired electrons. And paired electrons, they have spin in opposite direction. If one electron is spin in clockwise direction, the other will spin in anti-clockwise direction. And again, you have to remember that electrons of same orbital, electrons are same orbital, will produce same amount of magnetic moment, but opposite in direction. Why opposite in direction? As I told you just now, that they spin in opposite direction. Therefore, they cancel each other. That means magnetic moment produced by one electron will be cancelled by the magnetic moment of other electron. Right? Because the value will be same, but their sign will be different. If you consider +2 and -2, the sum of these two will be 0. In the same way, the magnetic moments are equal but with opposite signs. When we add the resultant of these two magnetic moments is 0. Therefore, resultant magnetic moment of paired electrons is always 0. Whereas if even if there is one electron which is unpaired in a particular substance or element, its magnetic moment will not be nullified, or the resultant magnetic field it will not be 0. Therefore, when we have such a situation where we think or we assume that the magnetic properties due to spinning of electrons and paired electrons will not show any resultant magnetic moment, then we will be having two types of substances on the basis of magnetic properties. One is called diamagnetic substance, the other is called paramagnetic substance. Actually, there can be paramagnetic, diamagnetic, ferromagnetic, etc. But mainly these all these substances can be divided into dia and paramagnetic. And what is diamagnetic substance? Whether it is element or compound or ion. A diamagnetic ion or diamagnetic compound or diamagnetic substance is that substance which have all paired electrons in their atoms or ions. Every orbital will have paired electrons. So there is no single unpaired electron. As I told you just now, paired electrons will show resultant magnetic moment as 0. Therefore, in diamagnetic substances, the resultant magnetic moment of all the electrons will be 0. Or in short, substance having all paired electrons is called diamagnetic substance or diamagnetic ion or diamagnetic atom. Now, second thing is the resultant magnetic moment is zero. Third is the substance, this type of substances are repelled in external magnetic field. Whenever they are put under external magnetic field, means they are brought nearer to a magnet, they will repel. Okay, just now I told you the properties of magnets. Repulsion and attraction is again a property. If two like poles are there, they repel. Or here, because they have all paired electrons, they are repelled. Next is paramagnetic substance. The substance which have at least one unpaired electron. There may be more than one unpaired electron, but at least one unpaired electron should be there, so that a substance is called as paramagnetic. So in paramagnetic substances, at least one unpaired electron will be there, whether these are in molecules or in atoms or ions. Okay, there should be one unpaired electron, so that is called as paramagnetic. And the resultant magnetic moment of these elements or compounds will not be equal to zero. Some magnetic moment they will have, it will not be zero. So remember, the paramagnetic substances will have at least one electron unpaired, and second, they will not have the magnetic momentum equal to zero. There will be some magnetic moment left behind. Third important point for paramagnetic substances is these substances attract in external magnetic. As I told you just now, diamagnetic substances are repelled, whereas paramagnetic substances are attracted. Next is magnetic momentum. How to calculate the magnetic momentum? Magnetic momentum is represented by mu. For any substance, we can calculate the magnetic momentum with the help of this formula. Mu is equal to under root n into n plus 2. And the units of mu, that is magnetic momentum, is Bm or Bohr magneton. So the Bohr magneton is shortly written as Bm. Here, only one factor is there on which magnetic momentum is dependent. And as I told you just now, that factor is nothing but number of electrons which are unpaired. If one, that means here n stands for number of electrons unpaired or unpaired electrons. Here, if one unpaired electron is there, we substitute 1 in place of n. So it will be 1 into 1 plus 2, or 1 plus 2, 3, 3 1 are 3. So the root 3 is equal to 1.732. So the value of root 3 is 1.732. So it is about 1.732 Bohr magneton for a substance which have one unpaired electron. Okay? If a compound or an element or ion having one unpaired electron, this much is the value of magnetic momentum. So the magnetic momentum for a substance or ion having one unpaired electron is about 1.732 Bohr magneton. In that way, if we calculate magnetic momentum of different ions, because as I told you, the d block elements are metals and they tend to lose electrons. Therefore, in their ionic state, we can calculate the magnetic momentum in Bohr magneton. First, let us consider ion Sc3 plus, means scandium ion having 3 positive charges, means it lost 3 electrons. When it lost 3 electrons, it has 18 electrons, means all are paired just like organs. Now, the remaining electronic configuration of last orbit will be D0, S0. There is no unpaired electron, no electron at all. Therefore, 0 electron means root of 0 is 0. Here in titanium ion, 3 positive charge, 1 electron is remained. Therefore, it is about 1.75, which is nearly equal to the calculated value. Sometimes calculated value and experimental value will not tally, but it will be nearly equal. Here it is 1.75, calculated value is 1.732. So that is expected one, this is calculated. Calculated is 1.75, expected value for magnetic momentum for an ion having 1 unpaired electron is 1.732. So to one of the equal. So the values are nearly equal. In ion B3 plus means vanadium ion, which is having 3 unpaired electrons, 3 charges, positive charges, having 2 unpaired electrons. This B3 plus is having 2 unpaired electrons, is having 2.75 as the value for magnetic momentum or mu. Again, chromium 3 plus, it has 3 unpaired electrons. Its value for mu is 3.8. Now, Mn2 plus, which has 5 unpaired electrons, its value for mu is 5.96. For ferrous, which is having 6 electrons, out of these 6 electrons, 2 will be paired because there are 5 orbitals in D, so only 4 are unpaired. Therefore, the value is about 5.1. Again, in zinc, we know that in zinc, 2 electrons from S level can be removed, so we remain with 10 electrons. 10 electrons means all are paired, so there is no unpaired electron. So the number of unpaired electrons is 0, therefore the value for mu is 0. So let us stop here because the time is running out. So the remaining properties, we can deal with the remaining properties in next lesson. So let us stop here. We will continue in part 2 of D block elements, or that is the second lesson. That will be the second lesson for this. Why? Because there are many properties which have to be studied by us, but time do not permit. So let us stop here.